this talk I'm giving right here is actually lead into the next talk. We're both self-contained, but this one is designed to introduce you to some material. It's actually put in heavy use in the second talk. So, you know, so yeah, today we're going to be standing on the shoulders of giants. And sort of ironic given that most people attribute that notion or that phrasing from Sir Isaac Newton, but really it came from the 12th century French philosopher, scholar, administrator. So it's kind of ironic there, but that's not what we're doing. We're actually going to be looking at some tools of functional programming that are essential to doing some really getting the real benefits of composition and actually being able to write purely functional code. So strictly speaking, this is all we really need if we want to really get the full power of pure functional programming. We need the ability to take functions, pass them to other functions, have functions return from functions, higher order functions. So functions being first class, we need to be able to support closures, currying, we need mutability, compositionability, recursion, referential transparency, which is absolutely important. Functions that do the same thing on a given input X, regardless of over time or space. And last one's arguable types. As you can see, I'm kind of the types myself. But strictly speaking, this is all we need. Are these notions? So this, you can just take this and say, okay, that's it. I'm going to adopt a pure functional programming style. Well, we've had that kind of thinking before. If you look at this is a bit of MIPS code, and it illustrates that kind of thing of all I need are my nuts and bolts, and I'm going to run with them and actually write some large applications. And yeah, strictly speaking, all you need is the ability to manipulate memory registers, your CPU registers, and bits of memory, direct manipulation of words, bytes of data, system calls, branch of equals, that kind of thing. That's all we need, strictly speaking. Well, we kind of went beyond that and said, well, actually, it'd be nice to sort of make some of this apply some patterns and have some imperative constructs, if-else statements, while loops, name procedures, variables. So we made that leap and realized that we need these constructs in order to really be able to think at an abstraction level that's higher than directly manipulating the hardware at the hardware level. So for FP, where are these constructs? That's the question. And we have a few. There's been a few talks today where we've introduced the notion of a functor, which has a map operation, goes from FP to FB. And we talked about, and you've probably heard about monads, which is really, you see there's different names that mean the same thing. We have point pure unit, which is about taking a value and lifting it into a monad of M. So say value A to M of A. And we also have the flat map operation, which is also known as bind, where you have an MA, you have a function that goes from A to M of B, and then you do the flat map operation, you get M of B. So we have these pieces, very useful. We also have monoids and semigroups. And interestingly, really a monoid is about, you have something that represents a base case, the degenerate case is 0. And a way of appending two of them together and getting another value as a result. So like addition, string concatenation. But the semigroup is actually, I point that out here because we use semigroups later on. Semigroup is simply a monoid without zeros, so you don't have a base case. So you can think of like appending to a stream or something like that, something where you don't know what your base case is. Now, a lot of these concepts seem like they might be vague. How do we use them really? And the reality is Dijkstra pointed this out very, I couldn't have said it any better. He says that abstraction is not about being vague at all. It's about creating a new semantic level in which we're being absolutely precise. And that's what we're doing. We're building up a vocabulary of functional programming constructs, leveraging the branch of mathematics known as category theory. And these are developments that have been made before. We want to mix and match and actually, allow us to actually do some amazing things with these concepts. So we're going to start by looking at sum types, right? And a sum type is, let's first look at Scala either, okay? So the Scala either is, the way, let's say like we're doing an averaging operation, you create a list of integers. And we want to match on what's empty. We provide an answer on the left-hand side. So either is saying it's your left or right side value. Everyone provide the answer to the right, which is actually doing the mean. Now, the reason why we return the left side if the list is empty is because you have a sum of 0 divided by 0. So that's an indeterminate form, 0 divided by 0. So what if we want to do two mean operations right here? We want to do the average of two lists and add them together. Well, it gets messy really quickly. And what's going on here, we have to basically listing out all the different cases. Or if the left is missing, or the right's missing, both are there, both are missing. And we have to have all of them. And that's really an indication that this subtraction didn't really buy us a whole lot. We want to get away from explicitly laying out all the different cases and have some machinery that does that for us. So what we need is a true sum type, right? That's basically what I'm leading into. And when you hear the word sum type, a lot of folks think like an arithmetic addition. And that's not really what we mean here. Category theory, it's best to think of sum in terms of, what is a product? So a product is actually, all case classes, they're essentially products. Because if you have, let's say you have fruit here, and you say your different values are apple and mango for the name, and then green and red for the color, well, you take a Cartesian product, you get all the possible values of this. That's why case classes is defined as a product. And why is it a product type? It's essentially a conjunction of different type values. The sum type is the it's the dual of the product. So that's why we call it a coproduct. So sum and coproduct can mean the same thing. And it is a disjunction between the values. Right? So, makes sense so far? So for that reason, that's why I say that Scala is actually it's a weak abstraction. It's a really poor sum type because you're not really fully realizing the subtraction that I'm talking about here. And an example would be, so the alternative would be to use disjunctions, which they're disjunctions in both Scala Z and CATS. And as we're going to see right here, they look similar to the Scala either. And they're both pretty similar to both libraries. And you see above, we use the symbols. It looks like a mathematical disjunction. That's why it showed that symbol originally. And it looks very similar to the Scala either. We say the left or the right side. And same with in CATS. We have a symbol there, but instead it's XOR, so it's actual alphabetical name there. So you say XOR left or XOR right. Now, the idea here is that now if we want to combine them, we can actually put them into a forward comprehension like this, which is really syntactic sugar for a nested flat maps and then a map at the end, right? You don't see a map there actually, but this is equivalent to like when you take a question and just put a map operation there. But that's equivalent to doing the forward comprehension. And so much simpler here because now if you have one of those values missing, you don't have to handle all the different branch cases anymore. This is handled by the machinery of the fact that this is a monad that we're dealing with here. And it's important to understand that it is monadic because disjunctions are treated as they're right biased, meaning that they're monadic on the right. You can do maps, you can do flat maps, and any operation that you do either of those operations, there's an assumption that you have a value there. If there is the left side, which is often used for error conditions, then it's as if you have an option and did a map or flat map and it was none. Then you know you're not going to, it's not going to do the apply the function to it. So now it's important to understand that since we're doing this as a series of nested flat maps, we're actually we have short-circuiting behavior. So if the first one is on the left side, then the second one, we're not going to actually get the second value so we can add them together. We'll just stop right away, and then the left side will be the result of all this expression. So that's important to keep in mind. The short-circuiting behavior is the result of this. Pattern matching works very similar like Scala.either actually. And you can have this also in cats too, but that's the Scala Z version. And here's Scala Z and cats. We can wrap exceptions we can actually wrap them with these different operations that are available to us. And this is great because what it does is if you have a value that may be able to throw exceptions, you can actually wrap it with these functions here, and it'll convert it to a disjunction. And this is much cleaner than you try catch blocks. I mean, it's no longer about having to deal with these exceptions bubbling up and where you catch them and shut. Now it's much cleaner, more elegant, purely functional approach to doing this. And yeah, so we're going to take a look back at this example again, and keep in mind that we're using flat maps here, and we're plugging map. Now that's actually really powerful because the flat map operations used in the context of a lot of things. I think I'm probably jumping a little bit ahead when I mentioned this. I mean, it's used actually for the free monad. We may have looked into that, but the monadic flat map operation is a very powerful approach, meaning it's very generic. And that's sort of the root of this short-circuiting behavior I was mentioning. So, and that's actually the cost of this power. So, we have to think back to a few principles. You might have seen some of these before, where first we talk about the principle of least privilege. It's really a principle in software security. You don't want to give too much privilege to a user. Otherwise, you might have, you could have malicious intent. You could have somebody, maybe doing something, intending just, write a database or something. Least privilege applies for security context. But that's the same thing as the rule of least power. It's fundamentally the same concept, where you're saying use the most powerful construct that you need to solve the problem. And what I'm getting at here is this example I provide right here, using monads is actually is a more powerful construct than we actually need. Okay? And at the cost of that, we have the short-circuiting behavior, which isn't always desirable. Like, say, you want to collect multiple errors together. Okay, kind of looking ahead there. So what we need something that is somewhere between a functor, which is FAFB, and a monad. We need something between those. Something in the middle. So what would that be? Well, look at the functors. They sit there right in the middle between functors and monads in terms of their capability. And you might be wondering, okay, well, what does this look like? How would that be useful? I mean, we want to basically combine both means together, adding them together, combine two some means which we're actually summing them together. How would it look? I mean, we could sort of postulate maybe it looks something like this. We have some dual functor, okay, where we say, okay, mean one, f of int, mean to some f of n. And then we have a function that takes in a tuple, the two values, and gives you a result. So you have this function right here, some dual functor where we're saying x, y, and then we pass in that closure right there, a plus b. So what we want is probably something that looks sort of like this, right? Well, in both Strelitzzy and cats, there is this apply trait, and this is implemented by all the different applicative functor types. And what this has the app, app2, and app3 methods, and that's the first one, by the way, being sort of a degenerate case. That only takes one. That's for a function that takes a single value and gives you a result. Well, that's the same thing as a functor. That's what that is. App. It's the same operation. But it's a special case of the generic idea of an applicative functor where you may have two values that you take in, f a to b to z, or three values, f a b c to z. Guess what? There's AP4, AP5, and it goes on to 22 actually. So that's the idea of a applicative functor is it's a generalization over the functor, so not quite as powerful as a monad, but a more generalized form of functors, more powerful than a functor. So this is how we actually use this in cats and Strelitzzy. We have the two mean operators right there. In cats, we do a map. We map the function on there, and then in Strelitzzy, there's no map operation. And you see in the first example, I throw 2 in there. I show if you have 2, or versus if you have 3. So you see how straightforward that is to actually combine these operations now. And that operator, by the way, there's all kinds. It goes by so many. It goes by home loan operator, TIE fighter, Cinnabon. I think I've heard some others. I forget what they all were, but pick which one you want to call it. Since we're not using flat maps here, there's no short circuiting behavior. Okay, this becomes really, really quite powerful. And it becomes really powerful when we look at sort of kind of the main killer app for applicative functors. And that's validations. Or validate if you're using cache. Now, so let's say, go back, we're going to have another function here, square root function, where we're returning a disjunction string int. And let's say we don't feel like dealing with complex numbers and we just want to return an error for that. That's fine, so we can do that. We write square root function that way. And we say, okay, we're going to use those as applicative. We say, okay, square root of -1. And we're going to combine that with mean of nil, which also is going to return error condition 2. Well, the result is just going to be 1. It's going to be the imaginary number is not supported. So it really just gave us the error for the first one. So you might first think, wait a minute, this short circuit again? Well, no, not exactly. That's not what happened. It's because the default implementation for applicatives there's something that we have missing that allows us to combine these multiple errors together. And if you see here the definition of validation, that something is a semigroup, which we talked about before. It's a way of combining errors in some generic way. So we have so the validation. You can think of validation as very kind of a more you could use that in place. Think of it as being able to be used in place of disjunctions for handling error conditions. And just like disjunction to the left is used for collecting errors, and the right is for your actual value of your result. So let's say we want to decide, okay, what's the type we want to use for representing our errors. We could use list, but I'm sure many of you have used APIs before where you get a result says error condition, and it's okay, what are the errors? An empty list. So that's ambiguous. And, we're talking about Scala, we're talking about using type safety being unambiguous in our types, and that's an ambiguity there. That's actually a poor choice of type is the reason, because you have an empty list of errors. Maybe it means that there weren't any errors, or it means that there were some errors, but well, I don't have any errors listed here. So that's why we have both CATS and SCSI have this non-empty list, which is a list that's guaranteed to have at least one element. So if you have the error case, you're going to have a non-empty list, so no ambiguity there. So let's take our mean example, our square example. We'll have both return validated NELs now. And it's very similar to before we had the either and disjunction types. But here we say invalid NEL, invalid NEL. Now, by the way, NEL, as you might guess, it actually stands for non-empty list. And I could just say validated and non-empty list and then string as the first type there, invalidated. I just said that. But it's so common that people will use validated NEL that they'll combine those together. So this is how it looks for CATS. And it's very similar for SCSI, also success and failure NEL. So now we do this, and boom, we get our result with all the errors combined. And that's how it looks in CATS. And you see that one and type. That's sort of a detailed implementation. It really it's I believe it's a subtype of non-empty list where it represents a single element plus a tail of additional elements. So I'm gonna show like a few neat things in shape lists that are also useful. These are some also useful tools. Kind of give you an idea of some useful capabilities of shape lists. They're actually I refer to them in the next talk, so that's kind of why I show them here. But also I think it's great sort of sneak preview of to motivate folks to take a look at shape lists, a super powerful library. And this is how Miles Sabin, the creator of shape lists, described it. I see it as a way of pushing the boundaries of Scholar's type system, defining the structure recursively. Now, this is, once again, it's just sort of an introduction. We're going to mostly look at H-lists for now. Let's kind of give you an idea of what's capable there. So we have like an H-list where you want to define, you can actually define the list of your types in the type system, kind of like an anonymous tuple. All right? Or sorry, it's like a tuple or, an anonymous case class, would be the way to describe it. So it's you say HNEL for the end of your type definition there, just as you'd say NEL for the end of a list, or NIL, sorry, NEL. And nil for the end of a list. So that's how you define it. And you can do matches like this where you actually have your data, so you match on the head and the tail, and right here we'll say, okay, we got the head, and the result is the tail right there. So yeah, that's H-list. And now there's also this notion of a generic, which is really awesome. Generic allows you to go back and forth between H-list and case classes. So we have a case class grocery item name cost double and name string cost double. And we just say generic grocery item 2, grocery item apple 0.10. And here it converts it to a shape list. An H-list. Now we convert the other way, res9 is random rebel, and then we actually get our case class back. So this is great for being able to handle different types of data that have like similar shape to each other, and sort of, you can see the inspiration why they call it shape lists. I mean, it's a way of manipulating data through the type system. There's a lot of other capabilities of shape lists I don't really have time to get into now, but just to give you an idea, you can flatten tuples, convert between tuples, this H-list, transform between generic types, then process H-lists and arbitrary size, recursive implicits. I mean, there's all kinds of really cool things you can do with shape lists. So yeah, this is really just kind of give you an idea of a lot of the really powerful features that exist, ideas that were received a long time ago from category theory that are now part of libraries like SCSI and CATS. And there's definitely a lot more to the journey definitely continues with this one. So, does anybody have any questions?
Will you post your slides?
Sorry?
Will you post your slides?
Yeah, they're not posted yet. I keep an eye on Slack. I'll try to figure out where to post them. Yeah. So, any other questions? Yep.
Can you elaborate more about what practically each list is going to allow to do that you couldn't do before?
So it's a way of how to describe it. Think of like a tuple where you say you have a tuple where you have different items in it. You want to actually say, I want to get all the last items except for the first. Like if you're doing it on an actual list, right? You could do that with an H-list, but you can't do it in a tuple.
Why do you want to do that?
Well, the reason why you want to do this, it's used in a lot of places where you're doing conversions from different types, and you have different case classes, for example, that have the same name, different names, but have the same kind of data in them. You want to line them together, manipulate them in some common normalized form, and convert them back to those types. That might be one place where you would use it. It's very, very powerful as you're building this. I find that shapeless tends to be really handy when you're building libraries, where there's a lot of functionality underneath the covers that go beyond, that require a lot more type manipulation that you would normally have. Does that kind of make sense? Yeah.
So a lot of times, the solution I've seen for that somewhat unique problem has been Monad transformers. Can you go into the reason why you would switch from Monad transformers to something like what you got on here?
Monad transform, that would be a more, because that you can transform from any monad to any other type of monad. So you can certainly do that too, but that's probably more heavyweight than what we need for here. That would be if you're going to maybe 3 or 4 other types of monads maybe, or maybe just more complicated forms than this, because these right here, you probably don't really need to use monad transforms with them unless you're transferring to another monad that's significantly more complicated. All right, any more? All right, I guess that's it. Thanks. What was the last time? Was that 1 minute?
That was 5.
Oh, 5? Oh, I'm a little bit of So I'm doing the next one.
Oh, you are? Okay.
I know. Should I go and come back or what?
If you want to take a 5-minute break or something.
Okay, I need some water.
Okay. I can get you water just outside the door.
Okay.
If you want to walk around, that's fine.
Okay, then
Screen things, I tried to change my Yeah, that's what everyone else is going on. It's like, oh, no, no, this I'm gonna fix later. This a parcel. So you can really tell it. And then after I do that, I use would have been great. And then, so every node has all this information. Yeah. At first I was reading from a file, but it's taking forever. So I wrote a program to do that and then print that out. That is the entire table of stuff. But yeah, right now the only thing I've got to work with actually is composition. Like over agency calcium,
Sorry? Okay. I'm just setting this thing up. Well, the idea is really actually building expressions, DSLs, building both their semantics and syntax in such a way so you can compose expressions together from expressions that will be able to take data from one n untyped or weakly typed sources and feed it through your expression that's actually purely functional, and is actually it's fully typed, of course, and gives you a result that's actually typed. And you sort of a way to visualize it is you have various sources where you have values of any, and you want to feed you through these functions that are composed together and actually give you a final result that's strongly typed. That's our goal. So some examples of some expressions that we might have might be like, say, I want to take the length of, the string Shostakovich, add 5 to it, compare it to 47, okay, the result's true. Now, let's say we have these values coming from sources generate exceptions and error conditions of some kind. So you have one error condition might be Kobayashi Maru, and the other would be, Khan. Add the length of that to the other error condition. Well, that's obviously, you can't, once you have these error conditions, you can't actually evaluate the expression, so instead the errors are combined together. Or you can have expressions themselves where the operations actually generate error conditions, like we have divide by 0, for the simple example. So let's say that we want to build our expression in our own syntax that we're going to be able to find ourselves, where we say, okay, ampersand or string concatenation, and we have these different symbols that represent the pieces of data. To have like A, we want to string concatenate with this reverse string B, and we concatenate that with a substring of C. And we have this right here and we take our weekly type source, which here we'll say is a string map from string to any. So weekly type, right? And then we actually pass it through our expression, and we're going to get the result. So this is an example of a type of expression that maybe wants to run, a very simple example. Now, we're going to be using some interesting tools today. Some of these I covered in actually the previous talk that I just gave, namely validated good functors, cats. We'll be using shapeless, a little bit of shapeless, we'll be using spire, and of course monads, and also Kleisleys. Now, Kleisleys you probably haven't been exposed to yet, so I'm going to go into what a Kleisley is. You can think of a Kleisley simply as a function from A to M of B, or A to M bracket B, lifted into the form of Kleisley MAB. And that is really a general case of the reader monad. The reader monad simply is really just a Kleisley, just that ID is the M. And that being where, for reader, you're simply interested in reading a value. That's kind of what I call reader. You can see it's reading a value from some source. And ID being just sort of an identity type that's it's the identity that represents itself. It's kind of a degenerate case of a type with a hole in it. So let's say we define two Kleisleys. We would say, okay, one Kleisley would be the length Kleisley. It takes a string and gives us an integer. You can go down option pure, that's not length. This is all in caps, by the way. The mappings to Scalzi are very similar. So, and I'll point out a few differences here. They're like pure and cats point in Scalzi. You can also say sum of S dot length. That would work too. So we're saying, okay, we want this return. We have a Kleisleys that determines if a value is even or not. So some IMAP, and closure is modular 2.0, and or modulo. And then what we want to do is we say, okay, we want to compose these together. So you can do composition just like regular functions with Kleisleys. And in cats it's a dot run, it's apply, it's called Z. And you would say, okay, the length, let's say we have the string, the length is even, exists identity. Well, that's true. It's an even, it happens to be an even length string, so that will return true. That's an example of that Kleisley's sort of a higher order form of a function. And you can compose them together. We can say we want to combine two Kleisley's together by, or we want to take two Kleisley's and feed an input into both of them and get results for both of them. Here we are. We take we want to repeat the length and reverse the string. And you can actually do that with a simple for comprehension. And we want to inject enterprise into our microservices. So instead of doing that, let's use Kleisley's. You use Kleisley's in place of identity injection. And this is sort of an example. Here we have this abstract notion of a loader and a writer. These aren't fully implemented here. It's just kind of give an illustration of some concepts that are, quote unquote, injected. You can have defined a sample store and say, okay, we have this task we're doing, the for comprehension to combine these operations together. Notice I'm using a Scalzi task here. That's what I recommend looking into if you're starting with using Scalzi strings. So actually that should be Scalzi string on task actually. So yeah, you can actually propose your Kleisley's that are quote unquote injected pieces of functionality, and and achieve the same results. So it's much cleaner than using something like, juice or, spring, or even something like, like a kick pattern, for example. Glycides are a much cleaner approach to that. So, okay, so now we get an overview of glycides. We're going to jump in and build our expression DSL library. So it actually comes into three parts here. We're actually going to talk about defining a library of operations that we want to support, a way of composing these operations together to form an expression, and a DSL syntax. Now we're going to define some core definitions. We're going to define an error condition simply as a case class, the eval-fold. Let's say it's a symbol on a string at the end, to sort of give you details about the error condition. It's a very simple way of modeling an error. It's just for us to look at. The notion of a term represents a value that's going to be fed into an expression and also, fed into an expression, also result of an expression. And that is a validated NEL, which is it's the applicative functor validated type, non-empty list of eval faults, and some value type. And then we have this notion of an expert expression, A to B, which is really precisely a term A to B. That's really handy here because now what we've done is say, okay, we're defining a way to say an expression that takes in an A, gives you a B, and it wraps this in a validated NEL, so you have your error handling taken care of. And we have this notion of an M type, where really it's an expression of any day. This is the edge of the world right here, where this is where your expression is getting values from a database, some external web service, or something that's weekly typed. So we want to follow the types here. That's going to be a recurring theme to this talk, is we're going to be following the types. And we're going to be taking values of NA from the external world and mapping them to X for source result, where the expression takes in a source and gives you some result value. So let's start defining a library of operations. And I'm going to be using some of the composition machinery that I'll be showing later, so some of these might not be clear right away, but I'll be explaining each of them. So let's say we want to define a concat operation. Now we're using shapeless here to identify the fact that, okay, for a concat operation, we're taking two strings and return a string as a result. And we have this lift2 operation, which I'll explain later, but the function in here takes a left and right value and uses a validation or applicative way to combine L and R and actually concatenate them together. So pretty straightforward, right? We have reverse, which this is a lift1, and it takes in a single string, usually a string as a result. It takes the string and maps it to not reverses the string. Now we have some actual arithmetic operations, add, minus, and multiply. And here we're actually using spire, by the way. The numeric is actually in spire. It's a way of being generically like to deal with integers, doubles, floats generically. And because since we're this you're in the numeric type class here, A can be an integer, can be a double. So Spire gives us that capability. So you don't have to define multiple versions of this for each different type of numeric value. So here it's very similar. We have different operations. We're doing addition, subtraction, multiplication. Now we're going to do division. Division is a little bit different because division, well, it's very similar in that we have this function that does the applicative on there, combining them, doing a division operation. But there's also this other function that is actually checking to see if we're trying to divide by 0. If we are dividing by 0, then what we actually have to do is we're recomputing the H list and putting an eval fault in there saying divide by 0. I'm not using the string here, just about that empty, and say it's invalid, invalid NEL. And what that does is that's going to actually get fed into the function that's passed in here also. Or, yeah, the second function that's passed in. You have an air conditioner will get fed in here, it won't get a value, and okay, the air conditioner can't do division. So that's composed lift 2. And then for negate, it's very, very similar here, we're just doing negation right here. So this is this sort of example list of library of operations that I've defined here. So what's the deal with these lift in and composed lift in functions that I was telling you about? Well, let's follow the types. We're taking a function that's of term O, not H and IL, okay? And gives you a term of A. Lift 1 has the effect of inverting this, or actually not inverting, sorry, lifting this into an expert type, which is into the validated type. So it'll actually give you an expert of O, H nil, and A, right? That's what lift 1 does. Lift 2 does the same thing, but it does if you have if you have a left-right term, which are, once again, these are validations. It'll have the effect of lifting this so that the outside is now the full validation, it's the full expression, going from LR, H nil to A. And composed lift 1 is very similar to lift 1. Only difference is you notice that we have the F parameter as another function. And what that does is that takes in term O, H, and IL, and then returns term O, H, and IL. So it has the effect of taking your arguments into this operation and trying to see if it's an air conditioning, and then passing along to the next function. So the result from F is composed with G. You probably guess at how the implementation of proposed lift 1. And proposed lift 2 is the same thing, just with area 2. Now we have the code for lift 1 and lift 2. And what it's all about is about using Plicely here, where what we do is we take the function term O, H nil to term A. We want to return an expression of O, H nil to A. We do that by creating a Plicely that actually matches the type that we want to return. All right, which is, once again, the input being Plicely with the input of O, H nil, A, O, H nil, and then A being the result. And you define that simply by saying, okay, well, that's your input. It's do a case match on that, H nil, so we did an H-less match right here. And you say, okay, we're going to take the function that's passed into here and do an applicative pure on that, the operand, and create an H-list, and then pass that to the function. So that has the effect of inverting these terms that are actually applicative themselves, inverted so that the entire thing is an applicative. That makes sense? Lift 2 is very similar. Only difference is for two arity operations. And I say LR because it's a binary operation where you have left and right operands. We take L and R, we take the left and right operands. And we're doing the same sort of thing here. In fact, look at the implementations are quite similar. We're just doing a pure on both ends and putting them together into the H list. Composed lift 1 and composed lift 2, these are very simple. All we're doing is we're doing lift 1, you see lift 2, but we're doing this composition of the functions, F, M, and G. So you could probably argue you don't really need these operations, but it's kind of nice when you define your library just to kind of use these built-in composition capabilities for you. Now, you might think, oh, can we unify these together? Can we unify lift 1, lift 2, unify composed, lift 1, composed, lift 2? And the answer is yes, you can, and that makes it a more advanced H-list, more advanced usages of H-list and shape list. We don't really have time to get into, so this would actually be a really fun exercise for the unconference, I guess. Possibly start combining these together. you have to sort of define a base case and sort of inductive case for these, so that you can actually combine these together. But yeah, I can't get too much into that for this. But it is possible to combine these together using shape lists, which is why you're actually using shape lists here to begin with, actually. So let me try to let's look again at the types that we're dealing with here, these different proposed operations. And once again, we have a length expression, okay, that takes in a string, single string, and gives you an integer. We take in the string, okay. Well, this, in order to actually compose these together, we actually have to, we're using list one right here, okay? And we're starting with this function that's defined in our library that takes in an S, H list with S. It does a map.length. And as you can see here, that's what list one does. It actually converts this, you pass it this function, term string H nil. It gives us a term int right here. And that's where, pass it the function, it goes from term string H nil to term int. It gives us an expression of string H nil int. And that's exactly matches the expression type that we want here for the length. And also we want here the expression in double, this is what we want actually for adding values together. We're taking the length from the result of the last expression and then taking some other value from external source and combining with that and adding them together. And that's where we get our expression for adding them together and get a result. So that's really what this is about here, is we're trying to have a way of taking these closures that represent our library operations and do a mapping onto these composable expressions, which is the type experts right here. That's the idea. So the dollar number, those are actually what I'm referring to as our edge of world. These are our values that are sort of external to our closed expression. And the way we're dealing with them here is we actually have, let's say I have a map adapter. And this is, before I was talking about this notion of a wiki type map, where we have our keys to any values and keys of type string. So yeah, we're just making this a simple map. And we're defining some implicits here. That we have a string in implicit, and we have a double in implicit right here, and we also have in implicit. So you have to define these different implicits to actually have the ability of reading from these, or actually has a way of taking this in of a type and actually giving us a value that we're actually reading to feed into the expression. So you notice right here we have the read operation at the bottom right there. And that's where we have let's say if we want to read a key or read a value of type A given a particular key, that's where what those implicits that are up there actually are used to supply for the read method. And that actually will actually read the map and give us a value. If it can't find the value, it gives us a key missing false. It's a part of our standard error handling that we're doing. And so yeah, so that was defining the adapter for dealing with that source. So that's all the code we need right here. That's pretty much it. And if we want to find the syntax for our DSL, well, what we need to do is we have to define these different readers that are actually using the read operation that we define in our adapter. And one thing you might notice is kind of a little bit funny here is where you have these implicit defs that goes from a symbol to the expert and then also to the number symbol expression class up there. And we have the same thing over here for string symbol expression. And the reason why is because we have some operations on that. That's on that class that we actually need to use. So we need to be able to convert to both. A little bit on the messy side, but and then we have a constant here, which actually lifts the constant into our expression form. And right here we have our different symbol operations. Say, okay, explicitly this symbol that I identified here, it's an integer, or it's a double, or it's a string. These are different string operations. That's a concatenation I tell you about, reverse, and then different numeric, arithmetic operations. Now, the value operations right here, they're kind of these are actually for evaluating, for value or expressions. These actually use a join operation, which actually has effect. If you look at join 1, we need to have the ability to take an expression from A to O output, and gives another expression where the output is actually a non-empty list. That's what that's all about. It's about joining into a single non-empty list result. Same thing over here in join 2. Now, the val 1 and val 2, they have the effect of where we have an operand, we have our operation, which is our library operation, okay? And we want to combine the two into an evaluation where it'll go from your original value to your final result. Okay? So we're using eval is sort of the bridge. That bridges the gap between your expression, which defines the two endpoints of your operations that are all composed together, and then bridges that into something that takes an entire input of your source type and gives you your final result. That's what the evaluable operations do. And I could give like a real, this is sort of the reader type that shows the first part of this, where you say, okay, we're reading in, next we're source the string, and we have a val, and we want to take this library operation of X for a string to int. And eval, what it does, it takes in both of those, and it gives us our final expression from source to int. Sort of composing this whole thing. And then, once you do that, then this will actually work. You actually run this, you'll be able to run this expression, and you'll get values. And like I said, you could add, the method for adding operations to the library is consistent. You just follow the same pattern for adding operations to the library, and you can just build up your expression DSL that way. So, yeah, any questions? Yep.
Is the CATS documentation the best way to get started, or is there another source?
That's a great question. So CATS is the best way to get started. The CATS documentation, it is. The documentation is really good. In fact, I think some people will look at the CATS documentation to figure out how to do something that's called Z. Because they're really similar. There's just a number of differences in implementation and choices of, sort of design decisions there. But you'll find there's a lot of similar to both. And I'd say the CATS documentation is a good way to get started on that, for sure.